Thank you so much for tuning in. In today's training video, we're going to look at how to run the graphical user interface. So to do that, you should have already pip installed the project onto your computer and downloaded a local repository for our GitHub project onto your computer. And if you navigate into that GitHub repository and you open up the photoreactor GUI, then you should have a file that looks something like this. The name of that file itself might change in later versions of the project, but it should mostly look like this. So if you go ahead and you hit run on that, or if you want to run this file through command line, that's fine too. I'm going to show you what the user interface looks like. So here, I'm on purpose trying to throw this error of peak simple not connecting. And the reason for that is I already had a running instance of peak simple that I had connected to the GUI previously. So you'll normally hear a voice message come up giving an alert that you're trying to connect to the laser and you're technically setting the laser to 0 milliwatts, which is what gets run when you first start the laser. And you can see here there's a couple of errors for the GC is not connected, again because we had peak simple open before, and then the heater is also not connected because we currently have the heater box switched to off, so there's no electronic communication with the heater. You see that there's a couple of different readings that are being put out from all of our different GCs, MFCs, as well as from the diode laser, which again is at set to 0 milliwatts. So the voltage reading across it is negative since it doesn't really fit into the linear calibration. So you can go through and we've got different tabs. We try to always open to the live view so that you can kind of see the state of your equipment whenever you initialize the GUI in the first place. There's a printout at the bottom, which is identical to what is printed out in the console. So you can see here I have one of them and several that I'm working through with testing. And you can see this is an exact identical match, but just so that you can see any messages that read out from the GUI interaction in the main window. We print that out at the bottom too. We have a manual control tab where you can go through and you can click on any different setting and hit apply, and that'll set the condition of the temperature controller, your laser, your different MFCs. You can use this whenever you're trying to cycle gases through or even turn off the gas flow so that you can change out the reactor. And then I want to show you how to build an experiment and create a study. A study is just a compilation of experiments. That is what you ultimately want to run. So we'll get started with that here. You can click on this button, Add Experiment. And each time you do that, that's going to create a new experiment object in Python, which is its own Python object containing data and instructions on basically how to run an actual experiment. And then when you hit Start Study, it's going to run through all of these different experiments that you create. So you can create those with these tools below. You can also delete them. And you can set some basic information for the sample that you have. So usually I like to label my sample with some kind of date. So here is just today's date. And then you might also want to add in what kind of material you're working with. So 100% silver sample, and any other kind of like identifiers you want to put here. Then it's also important usually to record how much sample you're using. So I include an extra text edit here that you can use to update the mass of your sample in milligrams to whatever you'd like. That has some functionality with how data directories get built, and so your file names will have sample mass appended to it. And in the future, when we start to support rate calculations, we might also utilize the sample mass as well as like metal loading to determine chemical rates instead of just conversions. You can also use these buttons to search for calibration files and control files. I'm not going to show that right now, but it'll just open a simple file dialog. You can click on this button and it will search for either CSV files or .con control files. When you open a control file, it will load on to PeakSimple if it's connected. If it's not connected, then it's going to throw an error message. So speaking of PeakSimple, we'll see how we can reconnect with that now. So we can go to our version of PeakSimple that's not working. And the problem is that once you connect with PeakSimple once using the PeakSimple API, you have to sever that connection with the program before you can reinstate it. And I've tried to figure out fixes to this bug, but so far I haven't been able to find any great fixes other than to just send a message to say, hey, you need to close this window first. The window will reopen automatically if you have it closed, so I recommend every time you close the GUI, just close the PeakSimple window too. So we can close that window. It'll ask if we want to save. You can hit no. PeakSimple can sometimes be a little bit slow to respond, so if you do anything too quickly with it, it might not work properly. So give it a couple seconds before you open up a new window. And then it'll open up a new one and you'll see that it's there's a different control file loaded now, which is whatever default control file you have set up for the system. So now we have our new version of PeakSimple that doesn't have any communication connected to it. And if we go back to our live view, we see we still have a connection error. But if we hit reconnect here, it'll go through the hardware communication reboot process. It'll sever all the communications it has, and then it'll try to open all those communications again, just like when you open the main window. And so you should see, yeah, in a second back here that a new control file is loaded, which is whatever you have set for the default in your GC class. And now we should get a green light on our communication status after it finishes connecting with all the different pieces of hardware. So you can see some readout messages down here for the different pieces of hardware, kind of like their boot up messages. And now we have a green light on our GC connection. So if we were to go and flip on the heater, we could also reconnect with that. Just remember that with PeakSimple, you always have to close this window and reopen it before trying to re-engage with it. So back to creating experiments, we have this study layout with a list of different experiments that pop up as undefined. If we go to experiment design, here's where we have a little toolkit to help us pick out what kind of experiment we want to run. So we'll have several pre-populated options for the type of experiment, temperature sweeps, power sweeps, composition sweeps, flow sweeps, calibration, and stability test. Especially these first four are the most commonly used. Temperature sweep is one we'll start off with just to begin. They all work in a pretty similar way, except for composition sweep has a couple more tools to it. So for the temperature sweep, we enter in some values that are reasonable. We won't get any kind of like printout, like this empty space is for showing us what our desired sweep might look like. But it won't populate this until we put in something reasonable into this form. So we enter in some values. Right now, these have to be ascending in value to work. And then we get this printout figure for what that temperature sweep is going to look like, where on the x-axis we have the time that it's going to take. On the y-axis we have whatever our independent variable is set to. Here is temperature, because we're running the temperature sweep. And these X marks indicate where there's going to be a GC collection. So you have to come in here and set what your GC sample rate is. There's some interfacing with your GC control file to see what's kind of like the minimum rate that you can run. It says rate here, but note that that's in minutes. This is the total time that it takes to run one GC sample. So for each control file, you might have a different amount of time that you have it set up to run. And it'll pull that in and set that as the minimum value. And it should update how low of a number you can set here too. but pay attention to make sure that you're setting a reasonable number for the sample rate, as well as the steady state time and buffer time, which I'll explain in a second, to make sure that these two values are larger than whatever your sample rate minimum value is. You can change the number of GC collections you want to have for each of these different plateaus, each of these different data points. So you can set that to any number that you want. Usually you want to do more than one so that you can have duplicated data points so that you can get some statistics. But for especially long GC runs, you might not want to do too many of these samples. The ramp rate is the ramp rate on the heater. We've got an auxiliary tool that you can check out on the Redox page about how this, you can test out the different ramp rates to see what your heater's performance is. The default value we just set at 15, and that's fine. Now, steady state time is going to be the time from when the independent variable condition gets set to when you run the first GC sample. So it's this portion between this blue dot, which is the first set point, and then this orange cross, which is the first data collection. So you'll see if I change this value, it pushes that X along the path, giving more and more time between when you set the first value to when you collect the first data point. So again, you just want to make sure that whatever the combination of this value and the next value is higher than what your sample rate is. Now, finally, buffer time is going to be the time between when you take the last GC collection, when you start the last GC collection, and then you stop that segment of the run. So if you look at the full experiment overview, when you get to the end of the run, you're going to ramp up the temperature or whatever independent variable you're varying to the next condition, and then you're going to have some steady state time again until you take the next collection. The time between you took the previous sample and you start the next one is the buffer time. So when the GC starts, it's going to be analyzing just the data that was flowing through the GC at the time when it started the collection. It doesn't really matter what happens after that collection starts because that's not what's being analyzed. So we can shorten our experiments by starting the next part of the sweep and waiting for steady state before we actually finish running that GC collection. But especially if you might be worried about some slight mismatch in the timing, you don't want this to be exactly changing over at the same time in case something gets out of sync later on. So you can set this to, usually I set just a couple minutes just to be safe that there's no kind of time delay that, if it happens, should only be on the order of milliseconds anyway, but out of precaution, I keep some value for this buffer time setting. So I usually keep this at about 5 minutes, and if I need to have a longer delay between GC runs, I usually like to increase the steady state time instead of increasing the buffer time. That way you're nice and confident that you're in a steady state position whenever you take your first GC sample. You always have to set some flow rate. So in the GUI that populates at 0, but that needs to be some value. And this is going to depend on what kind of MFC setup that you have. So if you have a different setup than what we do, you might need to go make some edits towards what some of these maximum values can be. Especially if you're not in a SCM range. If you're higher than that, then you might need to change some other values or even some of your units in the system. So you can set this to any value. We'll set it for just the 30 right now. And then the composition you can set to whatever you want. So these values will populate with AliCat's library. So this is everything that you should be able to click on if you were just on the kind of panel on the MFC. You can set these to whatever gases you're using. So just select what is applicable to your system. And then you want to set the composition that you're using for all of these different gases. So you can see at the bottom here, we're printing out what the sum of all of these are. There's nothing to check while you're planning the experiment if you're entering in a sum that goes to 100%. But once you start running this, if your composition value is not at 100%, it will give you an error and the rest of your study won't run. So you'll come back, to look at your kind of status of your experiment, and there'll be an error message because it checks and makes sure before it starts to run that these values equals 100%. But right now, the GUI itself doesn't do that checking. So the easiest way to kind of get around this is that we just print out what the value is. So you want to make sure that you're putting in something that equals up to 100% before you start the study. So that's how you plan out one experiment. When you go back to the study view, now you see that there's a name for the experiment that gives some of the defining characteristics of it. And when it saves the data, it's going to use that name that it generated from the experiment attributes to build this file name. And that'll be part of how kind of like the data hierarchy gets built. Be careful with where you save this data ultimately, because if your file names get too long, because we use some pretty long folder names and file names inside of some of how we save the data. If it gets to be too many characters, if it's really deep in some kind of data structure, then it might not save correctly anymore. So be careful with where you put this. Usually higher level folders is a little bit better. But you can go to pretty deep folders and still be okay. And last thing to notice is that when you switch in between experiments, you'll also change what this preview update looks like. So if you generate a couple of different experiments, like here, we'll look at power sweep, and we'll just make the most basic thing that'll show us a preview. If you go to your study overview, you can flip between and you can kind of see what experiments you have planned out. And you can look at how long each of these is going to take, and start to get an idea of how long your whole study is going to take. In the future, we'll implement a way to calculate the time and print that out somewhere in the GUI, but right now it's a little bit more of a manual process. And when you finally have implemented all the experiments that you want to run, make sure to delete any of the undefined experiments so that you only have defined experiments ready. Give a nice double check that you have the right conditions set, and then you can go ahead and hit Start Study, which I won't do here. But that will go ahead and perform all the different experiments that you want, and save data into a data directory so that you can analyze it later. And for the data analysis, you can utilize some of the tools we have in our analysis sub package to do all that analysis for you.